next speakers are joining us from this region. The title of the presentation is Examples of Smart Stamping Applications at Volvo Cars and BTH, Blekinge Institute of Technology. I will now hand over to Johan Pilthammar, PhD at Volvo Cars, and Mats Sigvant, PhD at Volvo Cars and BTH, together with Sravan Tatipala, licensed engineer at BTH.
Thank you. I hope you all hear me. We will, during the next 20 minutes, myself, Mats and Johan, give some examples of what we have done at Volvo Cars in the topics. And I'm happy to say that a lot of the things are well aligned with the previous presentation. We can take the next slide. Frequent visitors to this conference have probably seen this slide before. We have talked several years about it. We have done a lot of work in particular areas. We are good at Volvo Cars in material modeling. We have started together with the University of Twente to look at friction models the last years. Johan has finished his PhD on elastic tooling in presses and will talk about that. But we are lacking links between all these islands. And this picture illustrates the vision we have, that we will start with incoming material properties, label the blanks, be able to read that label in the press line, record press settings, and combine all that in data with the output, the result. And one of the examples I would like to show is the work of Sravan, where we took measurements on the top of the oil film variation on the incoming sheets. The oil is distributed evenly at the material supplier, but due to the transport, it's very often moved to the edges of the coil. And that in this study we model as a tailor welded blank with different friction properties in different areas. And interestingly enough, what we see when we compare a simulation with where we have an uniform oil thickness to a simulation where we have a varying thickness, and in this case we were also running an autoform sigma simulation, which means that we varied both process conditions and the oil film thicknesses. We see that with a varying oil thickness, the simulation becomes more critical. We see it to the left where we see the variation of the major strain in one of the critical areas. In reality, that variation increases. And if we look at the formability plot in autoform at the maximum blank holder force, we also see that the part becomes more critical. So this is one step of all the small bits and pieces we have to do to include in our models. And this was related to our running production. I will now hand over the word to Johan, my colleague, and he will talk a little bit more of another process, the die making process we have in Olofström.
Thank you. During the last 5 years, I have done a lot of research in one of these first areas that Mats presented in the picture with all the different areas around the press line. My area have been digital modeling of the stamping dies and the press machines and how they influence the forming of the blank. So to the left here, you see a stamping die from a CATIA, a CAD model. And these, of course, our plant here in Olofström, the main part is to produce parts for the car, but we also have a big department producing these stamping dies that you can see to the left here. So we are designing them, and we're also running simulations of them, and they are designed by input from, of course, how the parts in the car should look, but also restrictions in size of the press lines and different processes and how to assemble the parts after stamping and so on. And my part here has been to see how all of this influenced the forming. So to the right here, you can see how the traditional way is to conduct a sheet metal forming simulation. You can see the parts moving around here are the only parts of the stamping die and the press that's in the simulations today. So we are disregarding all of the structures in the stamping die and all of the flexibility and tilting and so on in the press machine. So we have the forming surface of the matrix, of the punch and the blank holder. But we are skipping that they themselves are bending. The process today is that we have initial design of the stamping die. You can look at the top of this picture here. So we design them, we run simulations, but we completely disregard that we have some bending and so on of the stamping die. So maybe we do some compensation based on experience or guidelines in the CAD software. Then based on the CAD drawings, we do the die manufacturing, we're casting it, and then we're putting into milling machines, and then we are using smaller and smaller tools, and in the end we're actually using just grinding and polishing the tools to get really smooth surfaces. And this manual rework, a big part of that is that everything is bending a little bit. So after tryout, we have some die surfaces that not looks exactly as they did in the final part in the CAD software. So what we would like to reach is the situation at the bottom here. We have an initial design. We have some simulation models so we can do this virtual rework in CAD and finite element software. And then we have a final design of the stamping die. That die is casted and milled, and then we can put it straight into the home line. So the ultimate goal is, of course, to skip the tryout, but we are aiming to reduce it at first hand. And then since we have something that looks in the real world as it did in the CAD world and the finite element software, we also have something that we can use for production support. Today we have stamping dies that doesn't look as they did in production. So now we have to scan the die and do a lot of modeling as soon as we get the question from the production. So what we have done in this research during these 5 years is building models that looks like this instead. These are how the simulation models look right now. So these are two pictures from the same simulation model. Let's see if they run. No. Is it possible for you to start the video? Now it starts. Yeah, so what you can see here is to the left is the blank inside the die, and this is in the model that you can see to the right. So the blank that's simulated to the left here is inside the stamping die to the right. So here we have the cushion in the stamping line. We have all the parts of the stamping die. The blank holder is there. Kissing blocks are included, and all the guidings between the different parts are there. It's also possible to include elasticity and the bending of the ram and the bolster as well. So here we have a model that we can use for die tryout, but it's also valuable if we in the future are going to build some digital twins or use data and simulation models to control production. And for all of this to work, also you need a good material models of the blank, and that is a big part of Mats' research area for doing material characterization, experiments for how to get this data, and based on that we have different yield surfaces and so on. So the more and more advanced materials we have and more advanced products, we need better material models and also different criteria for evaluating where we have cracks and wrinkles and so on. In the middle, at the bottom here, you also see something from a friction modeling. So material is a really big part. Physical modeling of friction is another part. And the third part is here what I've been working with. So these three together can be used to build digital twins in the future. Down to the right, Or of course, you can see up to the right here, we don't have the press. It's not visible in the model here. And it would be a very big task to model and simulate the entire press. So what we do instead is that we're measuring the press and then we're inverse modeling it. So we have just a surface or a simplified structure of the ram and the bolster that is behaving in the same way as the real press. So that's also quite a big part of the research we are doing. How do we measure the press lines? And when we get the measurement results, how do we do to include it in the simulation models? And also the model should be as small as possible. We started to build these models around 3 to 4 years ago, the model you can see here. And at that time, we run it on several hundreds of cores in a software called LicEng. And it took maybe 24 to 48 hours to solve this model. Nowadays, we have a model that I can set it up in maybe 1 to 2 hours, and then a model of this size can be solved in just 1 or 2 hours as well. So if we have the measured press lines, the die structure, and the forming surfaces, then meshing, setting up the model, and running it can be done in less than a working day. So a full virtual tryout of the, say, blank holder or punch or matrix can be done in a few hours. So the different parts of the simulation model, we are quite happy with that right now. Let's see. And we have done started to use this in tryout for internal dies that we make at Volvo cars. What you can see here is, you can see from below or from inside the die, the blank holder of a double action stamping die. And this is the same blank holder in the tryout line and in the home line. And the color here represents the bending or the flexibility of the blank holder. So you can see here that you have one bending of the stamping die in the tryout line and another bending in the home line. And this will, of course, give us some issues. If we are doing the tryout in the tryout line and then move it to the home line, we will get a different result after forming. You can also see that this is the pressure distribution that we predict on the blank holder surfaces. So depending on what press line that you're using, you get a slightly different pressure here. And also then if you compensate the surfaces, if you do a compensation in tryout line, it will not work in the home line and so on. And this is also from practical experience at Volvo cars. In this specific tryout press, if we do a tryout there and then go to the home line, we often have to do a second tryout to adjust it again. So these kinds of things we can now predict with these simulation models. So our suggestion for do these kinds of virtual tryout is to do the feasibility work with spring back and so on as you do it today in Autoform or LicEng. And then you can also do the spring back prediction and spring back compensation. When that is completed and you have the die and the spring back results you would like, then you turn on the elastic tools. You see what bending of the tools you get and you compensate it. So the hard part here is to being able to setting up this elastic model. When you're predicting the deformations of the die, it's quite simple to do these compensations. It's just, you see how much each node in the model is moving, and then you just compensate it with a simple script or something in the opposite direction. So you see here in the middle, these are both tryout line and home line, that when everything is bending, you're losing a lot of pressure in the middle of the blank holder here. And then after the compensation, you get some pressure in the middle again, and it looks almost as it does to the left when we're running with a rigid stamping dies in the simulations. So we have here a method for doing a full virtual tryout. Right now we have tried it in in-house production of stamping dies for double action blank holders. But the plan right now is to start to measuring all our tryout presses, so we can do these compensations quick and easy for punches and matrices as well in coming projects. So it seems to work quite good. It will, of course, need a couple of tweaks in the coming projects here, but we are on track to starting using these methods right now. And the final part in this presentation is a slightly different part, but connected to the first one here. We have done a lot of virtual modeling, finite element and so on, and measuring bolsters and ramps and so on. If all of this is going to be used in some kind of digital twins for production control in the future, we need to combine these models with measurements in the lines. Our suggestions is to measure drawing, forces in the press lines. We're measuring the incoming or get data for the incoming material, oil fill measurements and so on. And recently a student from Blekinge Institute of Technology, Andreas Andersson, also completed a thesis in our press line here. And it was also done together with Tata Steels. The project was to try to measure the forces in each cushion pins and during running productions. And this was done by mounting strain gauges on each of these pins and connecting it to a small Arduino computer. So with this, we can see the force in each pin here. You can adjust the shimming in the tool so you get an even pressure distribution. It has a potential to be used in kissing blocks and so on as well. So together with drawing measurements and everything else, this can also be a good technique in the future. An issue before with doing these kinds of force measurements and so on have been the cost, but what we did here was quite cheap. It's just a small part of the cost for the life cycle of the die. And the current issue here is at the moment this technique is working, but it took quite a while to mount all of these strain gauges on the pins. So we need some kind of technique to do this faster, or maybe that we can pre-mount and set up everything before we mount it in the die, because now it took some weeks. But the technique is promising. We can use strain gauges in the future to monitor different parts in a stamping die. Do you have anything to add, Mats, to our presentation?
No, not at this point in time. We take the questions in the. Maybe there's just time for a short question now, but otherwise we take it in the Q&A.
So thank you very much, Dr. Sigvant and Dr. Pilthammar now for this presentation. And also congratulations, Johan, to your recent PhD. Because it has been a great pleasure to working in this project together with you, as I actually have been doing for the last 4 years. And you have actually fulfilled my dream of being able to do this virtual tryout.
Yeah.
That I had thought of all my 20 years of sheet metal forming research. So thank you for that.
Yeah, thank you.
We will now.
We can mention that a lot of this research is done together with BTH and RISE and a consortium in Sweden in the Vinnova project.
Yes, and so I don't see any other questions right now, but Mats, you talk about data handling in your press shops, and are you already collecting a lot of these to actually start using AI, or are you already start using AI in your research here?
We are not at the point to start using AI. What we are looking at in the nearest future is actually to start make connections between all the data sets. It may sound ridiculous, but actually we are losing track of things internally. And that is what we are now trying to cover up. We can get data from the suppliers, we can do measurement in the blanking line, but we lose track of that information when it comes to the press line. So that loop must be closed, and then we can start working on this. And as I said in the beginning of my presentation, I very much agreed with Professor Havinga the previous presentation. I think this is too much complicated. It's too non-linear to do AI on this. We have to base it on finite element and then tweak it with measurements. That's the only way forward.
And we also have the approach of try to use our factory as the laboratory. We are including a lot of technique right into press lines and so on.
Yes, it's very great. And Mats used Autoform and Johan used LS-DYNA. One of the audience asked, and have you compared the results in forming simulations between the two softwares?
At the moment, for elastic dice, it's only possible in LS-DYNA right now.
But all the production simulations are done with Autoform.
Yeah, this is an additional steps that I'm doing after the production simulations are finished.
And our basic approach is to start out with Autoform, but like in Johan's case, we once in a while reach a point where you can't do it in the current version, and then we turn over to Dyna to get examples, verify that the research and the ideas is valid, and then we try to get it implemented into Autoform.
So thank you very much again.